All right, so we are going to today discuss an alternative to Gaussian elimination and LU decomposition for that matter. And here we are. We always have to change this type of presentation. All right. So basically, we have overviewed what are called direct methods for solving systems of equations. That means that assuming you have a perfect computer that is not doing any round of error, which you don't, but let's assume that you are, then in that case, you are going to arrive at the exact solution for the system. So the only error involved is actually that of related to basically round of errors, storage of numbers on your computer, and any errors that are involved in the actual arithmetic operations that you're doing as you're doing those denominations. However, those can actually get considerably large. And when you have a system that is like 1,000 equations or more, they can actually really impact the accuracy of solution. Plus, solving for them, it can take pretty long time. Okay? And we had some experience with how long time it can take even for 10,000 equations. So there are alternatives that are essentially looking for approximate solution, just like root finding methods, right? With root finding methods, we never had an exact solution that we got. We just got close to the solution. And we controlled how close with that epsilon, if you remember. Okay? So in that sense, the similar thing can be applied. So what would be the type of the method? How can we look for that solution to be close? So here's one example that is actually similar to those root finding methods. It's just now for a system. So these we call actually iterative methods because I'm going to iterate a certain number of times until I get close enough or my error gets small enough. So those are the alternatives to Gaussian elimination. So I'm going to start from some guess. I'm going to call that guess x0. And I'm putting this 0 in the notation up here, okay, as an so that it's not a 0th element of vector x. It's actually sort of like naming for this vector. This is my 0th vector, an entire vector x. So this is my starting point. So let's say that I have a problem that's like 4 by 4. If I rewrite these equations, so let's look at this first equation, okay? I can actually write this equation as x1 is equal to b1 minus this entire sum. Oh, wow. So I have to watch here because I am what I'm showing here on the computer is not related. Interesting. Okay, let me gauge. Okay, if I express x1 from here, which is hilarious because your video will be off, by the way. So it's just showing things differently. Or maybe I should just not show. Hey, I'm tall enough for this one. So if I express x1, it's b1 minus this sum here, and then divided, there we go, divided by a11. Okay? So basically that's what's shown right here. And I can do that then for x2 right here. So it's b2 minus all of the elements except for this one, right? And then divide by a22, and so forth. So this form here, okay, shows a way that I could use to iterate. I could take that first guess that I have and plug in the values that I have for x1, x2, x3, x4. It's a vector, right? So I plug in those values here, and this could be what I call my next iteration, my next guess. And I keep going, and hopefully I converge, right? And why do I hope that I will converge? Well, technically, I have used my starting point equations to kind of come up with this iteration, right? So this kind of system, it satisfies my starting equation. So maybe it's okay. Maybe it will get there. And indeed, there are cases where it's going to get there. We actually can gauge whether the matrix A coefficients are good enough for that. And in those cases, that is an alternative for solution. We call this method Jacobi. So let's actually, I can actually formalize what I see here. Would it be, now actually it's too late. But technically, does everybody recognize that every x1, x2, x3, x4, I'm showing it as xi here. So I is 1, 2, 3, or 4. So this my k plus 1 indicates my next iteration. Okay. So based on my previous iteration, which I refer to as xk, which was originally my x0, okay, then my x1 would be given by this. What I'm actually writing here is rewriting this just as in a more general way. Does everybody see that? So my xi, I have 1 over aii. Is that correct? Yes. I'm having x1, I'm dividing by a11. x2, I'm divided by a22, and so forth. Right? So that part is cool. I also have bi here, sure. Okay. And this sum here tells me I'm taking ith row of A, and I'm multiplying, I'm summing up and multiplying aij with xj for all j other than the actual I. Right? So I was doing that here. I took all of the elements in the first equation other than the first, a11, x1. I took all of the, in the second equation, I excluded x2, which is my I. Right? In the third one, for I is equal to 3, I excluded x3, and so forth. So I'm just saying, okay, do this sum, multiply, and sum up, except for I. Okay, all j's except for I. So basically from j is equal to 1 to I minus 1, and then from I plus 1 till the last one. Yes? Do we agree that this generalizes? Yes? So in this third equation, to rewrite it over there, I took this and I put everything else on the right-hand side. So my x3 is b3 minus a31x1, a32x2, a34x4. I skipped the third. Right? So that's what I'm saying here, skip the third. Okay. Skip the I for whatever I is. Okay? So this is a more general formula, but this one is relatively easy to type into a computer using for loops once you have it generalized this way. You're like, yeah, relatively easy. On Friday, a little less easy than on a Monday, but here we are, it's a Friday, okay? So essentially, these are the types of sums we were practicing for our exam 1, right? This is why. A lot of algorithms are actually written in a more general way like this. So if you're in practice of writing those for loops, you can just actually, even without understanding this formula and how we got here, you could technically implement it. Okay? So often that's how things actually work. You come up with this formula as a model, and then you give it to computer scientists. And computer scientists say, oh yeah, sure, we can implement that. Okay? Without even thinking what it actually means. Right? So there is two-step process here. One is actually modeling and getting to the formula. But second one is like, even if I just gave you this sum, which is what I did for exam 1, you're able to program it. Okay? So there is 2 steps to it. So let's actually do and get familiar with it. Let's actually, on the paper, work out this one before we start programming. So this is my 3x3 system, so it's a little smaller. Okay? And my actual solution, I've given actual solution. So I want you to take a piece of paper, rewrite this 3x3 system the same way That's what I did here. And here's the reminder of this is just to remind you of these formulas from the previous slide, which were done for a little larger system, but just ignore the fourth S. So rewrite the system in this form: x1 is equal to something, and then the second one express x2, and the third one express x3. And use that as a template for iteration. So I want you to start from 0, 0, 0, and then get my next iteration. So 0, 0, 0 is this starting point, this zeroth vector. So I'm going to actually write it separately so I can see how much time it takes. And to see that we get the similar results. Yes. Or you can just look at that system and rewrite it in a similar manner as this one is. So 3x1 is 7.85 plus 0.1x2 plus 0.2x3. And then divide by 3, right? And that's your x1 equals to something. And then do the same with x2 part. Did anybody get the first iteration? Is that a yes or no? It's a maybe so far. No? You don't know what to do?
Should we plug in for values of x?
0, 0. Right? So your x1 from first equation is 7.85 plus 0.1 x2 plus 0.2 x3 divided by 3. Everybody agrees with me? So then if I'm calculating this 1 from the 0, okay, I plug in these old values in the right-hand side. This is my first x2. Is minus 19.3 minus 0.1 x1 and plus 0.3 x3 divided by second equation divided by 7. And then my x3, so this is my new vector, x based on the old vector, right? Is from the third one, 71.4 minus 0.3 x1 plus 0.2 x2 divided by 10. So now I basically, on my right-hand side, I plug in what old values of vector x are. And I start from vector 0, 0, 0. Yes? So these three equations are actually expressing this just for k is equal to 0 here. But in more generally, I would have this for k plus 1. And this is then k, 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 k. See? So it's simply iteration is telling you how to get the new iteration based on the old one. So if I now start from 0, 0, 0 and I plug in 0, 0, 0 into the right-hand side, I have as my first x1, 1 in terms of the 0th one. I plug in 0 here, 0 here, so it's 7.85 divided by 3. Anybody has a calculator handy? I'm just going to leave it at 2.61. Okay. So x2 is, I plug in 0 and 0 into second equation, so it's minus 19.3 divided by 7. And that is minus 2. And then x3 is 71.4 divided by 10. Hey, I can do that without. I'm so good. I can divide by 10. After years of schooling. This is what I can do. Okay, cool. So now I have x1, x2, x3. Let's just quickly check how close am I to actual solution. Not bad, from like starting from a random guess. So let's now improve on that. Next iteration should get better if I'm converging. Okay. So now I plug in these three numbers, also here, to get my second iteration. This is where it is helpful to have a computer do that instead of you, but we're going to program it in a second. I'm not going to let you struggle and compute this. calculate x1, 2, x2, 2, x2, 3. So do that before we start programming. And we should get closer to the actual solution, though this initial thing was not too bad. That's my next step. So in any numerical solution, this is a numerical solution that is going to get to the approximate solution. You start with something, and then you improve on that as you go. So key thing in implementing the solution is to have a way to get to my what we call new iteration from the old one. Okay. So the way we figured out a way to get to the new, and sometimes you just kind of pull out a magic trick from looking at the problem. So the magic trick we pulled out here is we just took these equations and we kind of expressed x1, x2, x3, and x4 from them. Okay. And that kind of gives me an idea. Hey, let me put this old iteration and start from a solution set, which is 0, 0, 0 in this case, and put it into this right-hand side. And that's going to give me a new one. And since I came up with this magic trick, starting from the thing that I want to solve, I'm hoping that's going to work. Literally. Okay. Now, there is applied mathematicians have actually done the work and can tell us when is it going to work. I'm going to get that to the next slide. But it actually works. So a lot of times this was similar to that root finding method. If you remember fixed point iteration, we just kind of expressed our equation, one equation, as x equals to something else. G of x, x is equal to g of x, starting from f of x is equal to 0. This is the same thing. I'm kind of algebraically transforming it into x is equal to, except that right now I have a vector of x's. It's just not just one. It's a system of equations. It's not just one equation. But it's very similar to the fixed point iteration for root finding. So in any event, I gave myself a way to iterate. So now I'm just like, I put in, I can express my new iteration in terms of the old one. Because I have, here I'm using the same x's, so now I'm just saying old x iteration, I'm labeling it k, and the new one is k plus 1. And I can keep going, so it's going to be a nice little for loop. Yeah? So again, conceptually, every numerical method will do that. It's like, give me a next iteration, and then we're going to check, are we close enough? If we are, stop. If not, keep going. Yeah? Yes? So what did we get as this number 2? 3.
0.000 like 6.
Not bad, not bad.
So how did you get to the 3.006?
We plugged in this, and this value into this right-hand side and got my next iteration, which I say x1, 2, x2, 2. What is x2, 2? So that's pretty close to minus 2.5. Yes. And the third one?
And you plug that number into that, and then the third number.
So these two go into this one to get this. And then third one?
7.0061.
Pretty close to 7. So you can see that basically in 2 iterations we got really close. So that's way less computation than Gaussian elimination, which is what reduces error. But I got close. I didn't get precise. precisely the solution, but you're just close enough. Okay? So there is this trade-off between accuracy and having actual solutions. So let's get just quick comment. If I was programming this, there's actually the criterion for convergence is so-called diagonal dominance. Okay? So my diagonal element in absolute value has to be larger than sum of absolute values of all other elements in that row. And that has to be true for every row. So let's see. My 3, that's my diagonal element, is larger than 0.1 plus 0.2. Is it? Is 3 larger than 0.1 plus 0.2? Yes. 7, which is the next diagonal element, has to be larger than 0.1 plus 0.3. Is 7 larger than 0.4? Good job. And then for Friday, that's a great result. And then 10 is larger than 0.3 plus 0.2. Same here. I'm in the same boat. 10 is larger than 0.5. Okay? So for this system, it's going to work. And if not, it might, what we say, diverge. So it might kind of spin out just like a fixed point method. The proof why is a little beyond introductory course in numerical methods. Okay, so we're not going to get into the proof, but just to tell you, this is the how you check that this is actually going to work. Now, when do we stop our iteration? So I can visually already say, hey, this is pretty close enough. Okay. But basically, I have to measure somehow. Now, in this case, I actually know the actual solution. So I can check against that actual solution. But often I'm looking for the solution, so I don't have it. Okay? But I can take these 2 last iterations and see how close they are. And are they less than some epsilon? It's just that I actually have vectors. So I have to figure out how to compare vectors. I can use the norm of their difference. Yes. So it's not that I'm like just looking, are these 2 values close? I have to check that for all 3 values for my entire vector. So I can actually go one by one and check, is this one close enough? Yes. Is this one close enough? Yes. Is this one close enough? Yes. And that's going to be my yes. If one of them is not close enough, then I keep going. Or I can just use vector norms. We've learned vector norms for a reason. So vector norm is a way, norm of the difference should be small enough because I want that difference to be close to 0. So that's going to tell me whether or not. So again, either this difference between the 2 coordinate values, the relative error in it is small enough for all of the coordinate values in a vector, or I actually take the norm between 2 vectors and divide it by norm of my latest iteration. Is that small enough? Okay. So let's do a computational assignment. Create function Jacobi iteration that takes initial guess and A, B, and initial guess x0. And tolerance, okay? And does Jacobi iteration to find and return a solution of Ax equal to B. And I also want you to let x0 be an optional input. So this is now how to implement part. And I want you to test the system using the solution that we just computed. So I'm going to get you started. So this is going to be a function. And that function is supposed to return a solution. My shell of the function, nothing in there. So one thing, how do I first, this has to work for every size matrix, not just 3 by 3. Okay? So first thing first, how do I get the size of the system? How do I size up my A or B? Let's do len of B. Will that work? Should. And also, these are going to be matrices, so I better import my NumPy. So here's a starting point for you. Now, good programming practice would actually check all sizes of A, check whether A is square matrix, and whether the size of B is compatible with size of A, right? And if not, report an error. But I'm skipping that part for now. You do that after you work out everything else. You kind of spruce it up at the end, okay? And I can type in my A that I had just for practice. So I'm going to have to test this, I'm going to have to have an example. So I'm going to immediately type in my NP array (3 minus 0.1 minus 0.2). All right, so this is my Where's Gabrielle? That's her method, Jacobi. Give or take one letter. I think she's with a Y at the end, but we have somebody with the last name Jacobi in class. It's just it's a Y at the end, not I. See, she's actually famous for a numerical method, and you didn't even know.
They replaced it with the I because it's the iteration. It's the I for iteration instead of Y.
Oh, wow. Must be. All right. Technically, what you have to implement is this. Or you can stare at the empty screen. So. implement a loop that computes this from the old iteration, using old iteration. If it's easier to look at that, that can be your motivation. But for a general matrix, this is what it looks like. You have result in it. You have something you fix. Figure out something. Maybe you has figured out what you can work on during this weekend so you're not bored. You just don't
Thank you. Exactly.
thinking about you all the time. That time. Because otherwise you would just wouldn't know what to do with yourself, right? It's a problem with the operating system. You run everything else.
All the TAs, she said the TAs come in and teach occasionally.
Yeah.
Wait, why is this? Whoa.
Only this zero is not. So it's actually saying so the system is looking for what's on this block. For some reason, can't say it, so it can't connect it.
I can't have things like I used to go to
Right. But if you go to the
stuff like that.
system itself is fine. It's what the system is giving Jupyter notebooks as an information. For some reason, it doesn't why? Standard. So I would possibly just reinstall Charge. That should.
Let's see. I have 5 hours. No, we just jumped up to 28.
Oh, sorry. Yeah, you can't reinstall it. Yeah, try to reinstall it. For now, just save this. Joys of computing.
Yeah, mine's about
Are we getting anywhere with this? How many for loops do you have? Might be 4. So I'm gonna first set this error to 1 so I can just enter my while loop. What do we want epsilon to be? Something like this? I'm gonna iterate. So we're gonna set myself to iterate. So this way I enter. Now I need a for loop for I in range 0 to n. So I'm gonna call my, this is my comment to myself. X is my new iterations, sort of like k plus 1, if you will. And my x0 will be my old iteration. So based on this formula, here, I'm literally implementing it. So my XOI, my new iteration, is B of I minus sum. I'm going to figure out the sum in a second. Let me just write down the formula. Divided by A of I. Well, I have to compute that sum. But just by looking at this, do you agree with me? For all I. So for all I, my x of I is b of I minus sum. I'm going to figure out sum in a second divided by a of I. Yes? Yes?
Just we calculated for the like a number, a vector. It should not be like x and then the brackets like I, so like the first.
Right, but my vector is, this is the ith element of a vector, and this is my new iteration. So instead of having a k plus 1, I'm not going to record them all. Okay? I'm just going to have a new iteration, k plus 1, and an old iteration. That's all I'm going to record. Right? So technically, if you wanted to record them all, you could go and have a matrix that stores all of that, but that's a lot of memory for nothing. Yes? Oh, sorry. Yes, that's a great point. This is my leftover from a different programming language. That little detail. I didn't even notice what I typed in. It would tell me soon enough that I'm that I have a problem. All right. Now, I'm calling x my new iteration, my new vector. It's called x. So here on the left-hand side, I don't have it. I don't have x0. x0 is in here. Now let's figure out what this sum is. Okay. Oh, well. One thing that when I'm computing sums, which I can quickly type in, is that I have to initialize the sum with a 0. And then I have a for loop. So I'm going to complete this. We're going to complete this next time. But try to think about it. So compute this sum. So the point that I'm trying to get across is that even if this sum kind of scares you and looks complicated, write it down as sum, okay? And get the shell around it correct conceptually, and then go back and compute the sum, right? So step by step of what you see and what you know. I hope to see you on Monday. If not, I'll be here recording the class alone.